So, welcome everyone. This is NOC 25W110 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish from IIT Kanpur. I am a TA to this course. So, we go live every week on Saturday from 7 to 9. This is week 7. So, today we'll be discussing two aspects. One is the delay in inverters and another one is power. Two of the most important aspect in digital circuits. Along with this, the area will cover you the critical three aspect of the VLSI.
Sir,
Yeah,
so before you start, can you just explain the switching threshold concept once?
switching threshold.
The
So
from the PTC curve.
you have, this is your V in, this is your V out. So let's say if this is your inverter, so if this is your input, this is your output, and this is your VDD. So let's assume that everything is ideal for the moment. So you will have your BTC very steep window and something like this, right? So let's say this is your VDD, this is your VDD. So basically in digital circuits, what do we need to do? We need to, how do I say? We need to distinguish between 0 and 1, right? So there should be some region which you call it as a 0, right? And there should be certain region which you call it as 1. Now, how do you bifurcate that? Which point is from which point to VDD you will consider 1, and from 0 to which point you will consider as 0, right? So the common idea is to have a curve. You just draw a straight line with a slope of 1. That means along this line, your V in is equal to V out. Okay. And the point it intersects your VTC, this is generally called your VM. So why it is important? Because ideally what you want? Ideally you want your ideal signal will be something like this. Then your output will be, let's say this is input. So your output will be something like this. This is your V out, right? So the point at which your input and output are changing, or if for input and output to be equal, for example, let's say at this point, if they become equal, so that window of time is very little to you, right? But this is for the ideal case. That does not happen in the real world. In the real world, you will have your input something like this. There will be certain rise time and there will be certain fall time. So this is your rise time and this is your fall time. Okay. Similarly, if you see, your output will be, assuming that there is no delay, your output will be something like this. So these are the points that you consider as your switching threshold, or basically it switches from one state, the output switches from one state to the other state. Okay. So this point is generally at the voltage VDD by 2, generally. Okay.
Okay, sir. Thank you.
So yeah, so let's begin. So first thing what we'll do, well, so this problem is called sizing of inverter chain with respect to minimum delay. Okay, so first need to understand what is delay. Then we need to understand what is the delay for one single inverter. Then we will go for the chain of the inverters. Okay, so first question, that let me assume there is a circuit and this is, let's say, output, and let's say this is input, let's say some logic circuit. Okay, now for example, if it is a metal wire, let's say ideal metal wire, and you have a signal x of t, and output you will have a signal x of minus td. Td is your delay. So what will be the td in this case for ideal metal wire?
0.
So td will be 0. And what about if this wire is a resistance? Resistance with a value of R, let's say. What will be this td?
It will still 0.
Td will be still 0. Why do you say so?
Because the signal will eventually pass through the resistor. So there will be no delay.
So why, when will there be a delay?
If we add a capacitor with the circuit.
So basically, let's say this is your R, this is your C, and if you have some V in, or let's say x of t here, and x of t minus td here, okay, or let us just do it y of t, fine. So the point is, so can you tell me why do capacitor, why do capacitors introduce delay? What is the fundamental thing that it
Because
does?
so it's a storage element, right? So it will store some kind of energy within it. So it will introduce a delay.
So for example, if I just connect, just answer me this question. If I have a current source with a capacitor connected to it, what is the delay of this circuit? What is the delay of this circuit? If I have only a single capacitor, what will be the delay?
Is there any resistance or there is no
No, there
resistance?
is no resistance.
In this
Sir,
case,
I think 0.69 into C.
No, the delay is still 0, right? Because there is no resistive element. So only the capacitor is not sufficient to introduce delay. So that is the point I wanted to bring out. The matter of the fact is you need resistive path as well as capacitive path to introduce the delay. What capacitor does is basically it introduces a lag or lead between the current and voltage. Fine. This you might have studied in your 11th or 12th, maybe earlier of that also. So that 90-degree phase shift is nothing but the delay if you calculate it in time domain. Okay. So that is basically that whenever there is a current flowing through a capacitor, first of all, DC current does not flow through a capacitor, right? But in this case, we see that it will flow because it is connected to a current source, right? At the instant you switch on this current, at that instant you have infinite frequency. So you will have the capacitor shorted and the voltage will keep increasing across the capacitor plate. So charges get accumulated across the capacitor, right? It is simply your capacitor charging and discharging. So in summary, you need to have a resistive element as or the dissipating element of power and also a storage element in the circuit to have certain kind of to have non-zero delay. Okay. So in this case, if this is your input signal, so your output, as you know, it will be slowly charging, right? And this YT equation, you can easily write, let's say this value is 0 and this value is VDD. So YT equation will be VDD by 1 minus exponential minus T over RC. And the delay or time constant, you quantify it as R times C. Okay. This is the time where your output falls to 1 over E to the input with respect to the input. Fine. So you need to have a resistance, resistive and as well as a capacitive element in the circuit. So that is the basic concept. Then the question is, for an inverter, what are the resistive components and what are the capacitive components? So this is your inverter, right? So what are the capacitive components? First thing is that there will be a load capacitance. Okay, we call it as a load capacitance. Basically what is happening, let's say you have an inverter and it is connected to some circuit. Okay, some, let's call it some load. So this entire load you are modeling with a capacitor. Why are you able to do that? Why do we model the load with a capacitor? Anyone?
Because there is a gate capacitance present at the input side.
So whatever is connected, mostly you will see that some kind of the input stage of this load will be gate to a MOSFET. Okay, so there is no DC path of conduction. Fine. So whatever is connected after that, you can easily model that to a or lumped to a single capacitor. We call it as a load capacitor. Okay, so this is one capacitor. And what about the resistances? For example, so resistance model of a MOSFET. Okay, for example, you have a NMOS. Fine, and NMOS is on. So on has multiple meanings, right? What is the on state? One thing is that your VGS is greater than VTH, that you can say, but in digital cases we are dealing with only zeros and ones, right? So we'll simply say that it is connected to VDD. Fine. So if that is the case, then you can model, let's say this is your gate, this is your drain, and this is your source. So you can simply model this as a resistance. So this is your ideal model. Ideally, your channel should form and there should not be any resistance. But as you know, there will be multiple scattering event that leads to a non-infinite mobility. So that will lead to a non-infinite conductance and that will lead to a non-zero resistance, right? So this we call something as R on, okay? And this suffix N is for NMOS, fine? Similarly, what if I connect zero here or off? Ideally, what should be the model? So I will have a R off, but ideally I should have a open circuit. Whenever my VGS is less than VTH, is that okay with you?
Yes.
And what is the how? So this R off over R on is much higher than your one. That means your R off is much higher. So what is the consequence of that? So whenever there is a series combination of R on and R off, so you can simply ignore this thing, right? So what do we consider? We consider this for the on path and we'll consider this for the off path, off state. Okay?
Good afternoon, sir.
Yeah, same to you. So that is the case for an NMOS. Fine. So by the way, can you tell me why do I have this R off? Not R off is not infinity. Why do I have that? I had discussed this in couple of session back.
Because for the subthreshold current slope concept, we have a non-zero I of. So there should be a finite.
Exactly. So your I off is not zero. Okay. So this is the leakage current you have present in your device. We have discussed this in detail, right? So if you have a certain VDS, okay, and let's say you have a certain IDS that will give you your R of, let's say, at off state, fine. If IDS is zero, then only your R of will be infinity. But neither this is zero nor your R of is infinity, okay? But it will have a very high value. So let us keep that in mind. So the transistor model, how do we represent it, is something like this. So this is your gate, this is your drain, this is your source, and this is your R on. Is that clear? When your gate is 1, so this will be closed, and basically your source, between source and drain, you will have the on resistance. We'll go back to this one. And whenever this switch is open, so there is no current flowing between the drain and source. Basically, we have the open circuit. So we fall back to this case. So this is a way we will represent the transistors. Okay. PMOS is same, just the on and off condition is opposite. Okay. And for PMOS, we express it as, so this is will be your source, this will be your drain, this is your R on P, and we will have a this is your G. Okay, this is the switch resistance model of the transistor. Fine. So now what about the delay? So let's say So let's say I have VDD and I have, this is my V out, this is my V in. Fine. So let's say my V in is 0. What do I expect at my V out? I expect 1, right? So if V in is 0, that means what? PMOS is your at on state, right?
Yes, sir.
So this is your R on times P, and then you have your load capacitance here, CL. So similarly, you will have your CL here connected. And what about this bottom path? This will be open, right?
Yes, sir.
Because your NMOS is in, when it is 0, your NMOS is in off state. Fine. So now what will happen? So I see a charging path of the capacitor through this. Fine. So in this case, if this is my V out, so my V out will change from 0 to VDD, or my output will be 1. Okay. Similarly, if my V in is 1, then I expect my V out to be 0. So in that case, my PMOS will be at off state, this will be at on state, and I will have my load capacitance here. So whatever was stored in the capacitor or the load capacitor now sees a path to get discharged by the NMOS. Okay. So this is your V out. So V out will change from VDD to 0. So we call it the discharging of CL, and this one is charging of CL, and this one is discharging of CL. Okay. So now the question is, let's say you have an RC circuit. And this is your V in. So what is the equation of your V out? As we have mentioned that it will be VDD times 1 minus exponential minus time over R times C. Okay. Fine. This is the first order RC circuit where I am tapping the output at the across the capacitance. Another thing, let me define another thing. So let's say this is your time axis and this is your V in. Okay. And this is how your input pulse is changing. So as I have mentioned earlier, this time is called as, so in digital, what I wanted this, right? So basically the green one is your ideal input. Okay. This is how you want your pulse to look like. But the black one is your, what you get in actual or physical scenario. So this delay or this time is called TR, and this time is called TF. So TR is your rise time and TF is the fall time. Fine. So now how will your output change? So your output will change. Let's say output starts at this. So your output will, so let me just mark the points. This is your VDD. So this entire thing is V in of T. This is 0. Fine. Similarly, this is your V out of T. This value is VDD. Fine. So what I'll see that when my signal travels from this place to this place or this place to this place, basically signal travels actually from the power rail to the output or output to ground, but the controlling is by the input. So whenever I am applying some input, the transistors take time to switch, and that switching will take some time. That is why, for example, if I see the peaks, there will be a time difference. Okay, that is the propagation delay of the signal from input to output, or this will be valid for any combinational block. Okay, so now what we will define, let's say we mark these two time points in the time axis. So this is corresponding to 0.5 VDD or VDD by 2. Okay, similarly we'll mark the same points at the output as well. So this is your VDD by 2, and this time is basically the delay which should not have been present in the circuit, but this is the artifact of the physical world and we'll get this delay. So this delay is called TPHL and this delay is called TPLH. What does it stand for? TP stand for propagation delay, P stand for propagation, and high to low, HL is high to low and LH is low to high. So high to low and low to high means my output is changing from high to low. Okay, and in this case my output is changing from low to high. So always remember the nomenclature of the or the naming convention of the delays are with respect to the output level change. It is not with respect to the input. It is always with respect to the output.
Sir,
Yeah.
sir, can you explain once more?
Okay. So till which part you have understood?
That LH equals to HL.
Okay. So let's say you have an increase like this in the input signal. Okay. So corresponding to that, you will get an output. So inverter is doing what? Inverter is doing your 0 to 1 and 1 to 0, right?
Yes, sir.
But there will be a delay associated with that.
Sir,
So
but the input is curve, sir, but
input is,
input is showing
so this is your input, right?
yes, sir. Yes, sir. Yes, sir.
So input is changing from low to high. So corresponding to your output will change from high to low, right?
Oh, yeah, okay, sir.
But whenever your input is crossing the VDD by 2 mark, Similarly, your output will also be crossing the VDD by 2 mark.
But VN is
Yeah,
but VN is sir, but VN is 0. No sir, 0.5 no sir. But
Vin is 0.5. So that is the thing I have explained earlier, at the very first, right? So whenever is your Vin is at 0.5, what is this point? This point is called your switching threshold, okay?
okay sir.
So whenever you are at this point, what is your Vin and what is your V out? Your V in and V out are essentially the same, right? It is
Yes sir.
approximately equal to your VDD by 2. So this is the
VDD by 2.
line, that is what you are defining your switching threshold to be.
Okay sir.
So that is why while defining delays, we consider that VDD by 2 point and see that after what time my output is also at VDD by 2 point. But what is the difference in case of my input? My input is changing from low to high. Basically, think it in this way: your input is changing from 0 to 1, and at certain time you are passing the point 0.5 volt. Similarly, your output is changing from 1 to 0. Then also it will see that 0.5 volt, right?
Oh, yes sir. Yes, sir.
So the time difference between when input is passing that point and the output is passing the same point, that is called the propagation delay.
Okay.
But this
Understood.
propagation delay can be happening at the reverse end also, means your input can be going from, in this case for example, your input can be going from high to low, but your output is going from low to high. So what I am telling you, that the naming convention of the propagation delay, what is TPLH and what is TPHL, is depending upon the change in output. So in this case, output is changing from high to low. So that is why this delay associated with it is called TPHL, high to low. Okay. So if you understand this
Okay.
point while writing when we will write the formula, you will easily see that what on resistances of which MOSFET to be considered. Okay. That is the main
Okay.
point.
Okay sir.
So if that is the case, so now if I go from this place to this, and so let's say this is V out, right? So V out is when it is at VDD by 2. So this will be 1 minus e to the power minus this by RC. So if you simplify, your T will become 0.69 times R times C. So this 0.69 comes from the natural log of 2. You just simplify it and see. Okay. So basically this T is the time that the output takes to go from a fixed value, let's say VDD, to VDD by 2. Okay. So this formula is the exact case of this cycle, because here your output is charging, right? Your capacitor is charging, or output is getting from load to, this is the case, right? Output is going from 0 to VDD. V out is going from 0 to VDD. Similarly, if you write your V out formula in this case, it will be, let's say, initial value to be VDD times e raised to minus T over RC. Okay. Then also you will get back to the same figure. So now can you tell me what my TPHL and what my TPLH formula to be? So this will be something 0.69 times some resistance, some CL. This is also the same. So let's say this is also the on resistance we know. So can you tell me for TPHL which MOSFET is charging or discharging, or which MOSFET is at the on state? For TPHL,
NMOS will be on.
Sir, NMOS is discharging
and for
uh,
TPLH it will be
PMOS,
PMOS, right?
PMOS will be on.
PMOS, yes.
So just by looking at the nomenclature, you can simply tell if high to low means my capacitor or output is discharging, or discharging has to happen through the NMOS path, right? So that is why my NMOS has to be on, and that is why this will be R on of N. Fine. So and the propagation, overall propagation delay, TP is defined as TPHL plus TPLH divided by 2. It is the average value of the 2 propagation delay. Okay, so this is what is your, from delay point of view, this is what we got as the delay of the inverter. Now we'll analyze this further. For example, your TP is, now I can write 69 times, let's say R equivalent times C equivalent. Okay, we'll see that how this R and C are changing. So now our goal is to study this, and how does transistor sizing impacts these two. Okay, so let us take R equivalent first. So R equivalent nothing but the on resistance of PMOS or NMOS. Okay, so when it is on, my VD is also, for example, okay, so IDS equal to, what is the IDS linear formula? And what is the IDS saturation formula?
So mu1 C of W by L, VGS minus VTH, sir,
And go on.
into VDS.
So this is your linear region formula, and your saturation region formula is VGS minus VTH whole square times 1 plus lambda VDS, right? Now what is your R on? 1 over GDS. So can you see from the above formula, just confirm that. So let us make the mu generic. So this will be applicable for PMOS and NMOS both. So is this okay?
Yes.
This is the proportional sign. Okay. Others?
Okay, sir.
Fine. So your, what we note, that if my W by L increases, my R on decreases. Okay. So by the way, what do I want? Higher delay or lower delay?
Lower delay.
Lower delay.
I
Lower
want
delay. Lower delay.
lower delay, right? Lower delay. So I want my TP to be small. So for that I want my R equivalent to be small. For that I want my W by L to be higher. Okay. Because my mu is a mobility is a semiconductor property. It does not change much. But why did I keep mu in the proportionality as a separate quantity? Because we also have seen in one problem that mu n or the mobility of NMOS is basically twice the mobility of PMOS. Fine. So that means if my WP by LP is equal to WN by LN, so what about my on resistance? So on resistance of which one will be higher? Is that okay? Have you understood the notations? So basically your your this NMOS is related to TPHL. TPHL will be half that of TPLH. Is that okay?
Yes, sir.
So basically what is happening? I am telling you that mobility of your electrons are higher than the mobility of your holes. It is almost twice in case of yours. These are not, by the way, these are not the bulk mobility. Okay, bulk mobility of silicon is 1350 centimeter square per volt second. But in case of whenever your conduction is happening in the MOSFET, it is near the silicon dioxide surface. So there will be surface roughness scattering that we do not consider in case of a bulk or a pristine semiconductor bar of silicon. So in this case, the values will be much lesser. It is around the range of 300 to 500 centimeter square per volt second. Okay. You see that the surface roughness scattering has reduced the mobility in almost one third to what it is in case of bulk mobility for silicons. Okay. So this is, if this much you have understood. So this is, by the way, not desired. Okay. So we always try to have my TPLH equals to TPHL. So for that, what do we do? We just make my PMOS twice as that of NMOS. Okay, the size of PMOS we make twice that of NMOS. So this, and I have my mu P is equal to 0.5 times of mu N, and this two quantity leads me to TPLH equal to TPHL. Okay, so we have understood the consequence of increasing size or transistor size to reduce the delay, right? But there will be other effects. For example, so far we have not talked about C equivalent. We have considered so far C equivalent to be CL only, okay, or the load capacitance, but that is not true. So impact of transistor size on C equivalent. So let's say this is your inverter. And let's also draw one MOSFET. Okay, so this is your drain, this is your source, this is gate, this is p-type substrate. So what are the capacitances you can see in the MOSFET?
There will be an offset capacitance.
There will be an oxide capacitance. So let me just draw the 3D view for to better understand what is going on. Okay, let's say your drain side is like that. So there will be an oxide capacitance. So this capacitance you are talking about. And what are the other capacitances that can have? So this oxide capacitances is this capacitance, right?
Yes, sir.
And what about the other capacitances?
There will be some
Sir, there will
parasitic.
be a
There will
there will
be.
be a gate to source capacitance, gate to drain capacitance,
So
gate to bulk capacitance.
why that there will be gate to source capacitances? So gate to bulk is this capacitance only is gate to bulk, right? There will be a depletion capacitance. So this is what is C depletion and this is C ox. This is the gate to bulk capacitance, right? This is their body terminal.
Yes, sir.
So where do I see the gate to source capacitance?
So because sir, that gate is overlapped between the N and
So you mean to
the
say
both.
this region, right?
Yes, sir.
So as he has pointed out, so we have something called this portion we call this as LOV or overlap regions. Okay, why does it happen or why does it occur? Anyone?
I think sir, diffusion is not properly occurred there.
No,
So that's why
diffusion
that.
properly occurs because see what is happening. Let's say this is the exact edge you want to make your drain to be, and this is the oxide edge. Okay, let's say this is the oxide you have. Now you will have a window like this through which you will pull the you will basically put the, let's say this is N plus, right? Let's say you are putting arsenic dopant atoms. Fine.
Yes,
For
yes,
that
sir.
arsenic dopant atoms to go into silicon, so earlier what was that? Earlier it was silicon only, p-type silicon. So now you want
Yes,
that p-type silicon to convert it into N plus silicon, so you will have very high energy arsenic ions, right?
yes,
So you
sir.
will do ion implantation or you will do dopant diffusion. So for that you need to have high energy particle going in this direction. So that high energy particle when reaches this window, right? So it tries to laterally diffuse in these directions as well. So here you will have something known as STI. So that is nothing but your oxide. So it will not go into the right side direction. So here you have something called known as oxide. So there it is seeing a hard boundary, okay?
Yes, sir.
But in the left side, it will start to diffuse. So basically, however good, how much good your process can be, so there will be a certain region in under the oxide which will have this N plus diffusion. Okay, and this oxide, see this is your gate and this is your drain now. So you have a oxide capacitance like this. So this is your one of the CGD, or we call it CG or CDOV. Okay, so similar thing happens at the source side as well. Okay, so that is one case. And
Sir,
what about,
I have one question.
yeah,
Sir, that shallow trench isolation and the gate oxide is the same material or the different material?
material is same, silicon dioxide, but the process are different through which your oxidation process is done. Basically, how oxide are grown is basically you oxidize your silicon, right?
Yes.
So the gate oxide is basically at the heart of your device. That is what you say. That is the main thing that is controlling the field effect of the device. So that has to be that silicon and silicon dioxide surface. So what I mean to say is that this surface has to be very clean surface. Okay, as less as impurity or impurity states possible. It should be very the process to create this surface is very sophisticated compared to what you do in this region, because no transport is happening across this region, right? So transport is happening across the channel is at that position. So material is same but the process are different.
Okay, sir, got it.
Okay, so another thing is that, for example, this is my gate, right? And this is my drain. What is there inside? Let's say there is nothing. If even if there is air, so there will have some capacitance. Air is also dielectric, right?
Yes, sir.
Yes, sir.
So this thing is called CFR or C fringing capacitance. Okay, at very high frequencies, this also start to play a role, because we know that the impedance of the capacitance is 1 over omega c. If omega is high, however small your CFR be, that will lead a small impedance path or current will flow. This is called the displacement current. Okay, that appears in your Maxwell's equation. Anyway, so that is one thing. And what about the capacitances between this? So there is a diode, right? We have discussed this while discussing the body effect. So these diodes will also have some capacitances, right? What is the small signal model of diode? In reverse bias, if let us assume that this drain side is reverse biased, it will obviously be reverse biased. We have discussed this, right? So the reverse bias small signal diode model is nothing but a capacitances, right?
Yes, sir.
So there will be capacitances through drain as well. So now if I translate, and let's say that my source and body is shorted, okay? So this diode does not matter for the time being if we ignore the body bias effect. So if we try to see, so there will be a capacitance like this. These capacitances are your CGD. Then there will be a capacitance like this. This is your CGS. And let's say you have body contacts as well. So you will have body contacts here. So there also you will have your drain to, let's say this is your drain, right? So you will have this junction capacitances CDB, and in this case this CDB, right? And how does this capacitances scale with W or your area of the device? So this is your W, right? For example, if I consider this capacitance, so this have a this type of area. This is your oxide, let's say. So now if this is my W and if I increase it further, so does my capacitance increase or decrease?
Increase.
So your C, let's call it parasitics, will increase with W, because I know that my parallel plate capacitances are epsilon A by D, right? So by
Yes.
increasing the size, my parasitic capacitances will increase.
A
That
will
is what we, yeah,
Yes, will
that
increase,
is
sir.
what we understood. Now, in small signal sense, what is VDD? It is ground, right?
down.
So can I model my transistor inverter parasitic capacitances like this? So I will have a capacitance to ground, this drain to ground, and also this drain to ground. So basically what I have done, let us take this CDB. So CDB is between what? Between drain and ground, right? So this is my CDB. Similarly, this CDB is between drain node and ground node. So again, this will be from drain to ground or output node of the inverter to ground. What about the gate capacitances? The CGSS can be taken care of like this. What about CGD? CGD is connected between input and output, right? So CGD, so let's say this is my inverter and CGD is connected between input and output. This is CGDP plus CGDN. So can I ignore this and connect two capacitances like this? Do you know this thing? If there is a load or there is an impedance connected between the input and output, I can divide or distribute that impedance between the input node and the output node. Do you know this stuff? Because this we are going to do at later in this course, okay? But I am just telling you, do you know about this?
The replacing it with the two parallel capacitors makes sense because in parallel form they
No,
add up.
not parallel, no, right? It is between the two nodes. Let's say this is your input node, this is your output node. The capacitor is between these two nodes. Let's say there is a load between these two nodes. What I am telling you, you ignore this and connect a load between these two ground and connect this to ground. This is completely different thing. This is not parallel. So anyway, for the
That
timing
means
one,
sir, we are
yeah,
like we are input capacitance of the inverter and the output capacitance of the inverter. We are placing that to capacitance.
not input capacitance and output capacitance. What I am telling you, I have these capacitances, right? See, CGS, CDB are sorted because these are connected to a node to ground. Fine. But what about this CGD? CGD is connected between input to output, right? This node to this node. So how will I bifurcate this in between input side and output side? So there is something called Miller's theorem. I do not know if you have heard about it. We will do it in the course in due time. But you understand,
Sir, I have heard it.
yeah, it is very simple thing. Whenever there is a impedance between two nodes, we can distribute it to the individual nodes, right? By some, this will not be the exact impedance, but that impedance will be transformed by something related to the gain of that stage. Okay, we'll do that in when we'll do some of the analog circuit part. We'll do that. Okay, but for the time being, you understand that this CGD, this CGD, I am clubbing to this input nodes and these output nodes, right? So this input and output, this is my output and this is my input. So the capacitances I have shown in this figure includes the CGD as well. That is what the point I wanted to make. Okay. So now if I again draw an equivalent, so what will I have? I will have something input capacitance here, some output capacitance here, and I also had my load capacitance, right? I will have my load capacitance. So this is CL, and let's say this was my CDN, this is CDP, this is CGP, and this is CGN. So this capacitance will be CGN plus CGP. This capacitance will be CDP plus CDN. Is this much okay?
Yes, sir.
Sir, yes.
If this much is okay, can you tell me the delay of this inverter? What is my TP?
0.9 into
0.69
69
into
R.
let's say some R equivalent. This R equivalent will change depending upon your on and off, or if you take the average, it is the R on by R on N plus R on P by 2, right? Times, what about the C?
CL plus CDP.
CL plus CDP plus CDN,
CDN.
right?
CDN, yes.
Because from this node I have this and this in parallel, so capacitance is parallel, in parallel adds. So is that clear?
Yes, sir.
Sir, okay. Sir, sir.
If that is clear, so let me call this capacitance as C internal. Okay, this is just definition. Let me just change the color. And this capacitance, let me call C in. It makes sense, right? This internal, basically the internal delay, internal capacitances that creates your delay, and C in is basically the input capacitance of the inverter. So what I'll do, I'll multiply this with C in, this capacitance, and divide this with C in plus C internal by C in. Now, from the sizing point of view, let's assume that I want to check how my this impacts the delay. So basically what is happening? So let's say L is fixed. We are concerned about W. And that is mainly what happens in the industry as well, right? Because you do not like to play with the length, because length has, if you make your length shorter by increasing W by L, means if your length is very much shorter, you will face severe short channel effects. Okay, those things, if I do not know if the course has it. So basically what happens if you go short, where did I have, basically if you go short, your curves will look like this. Okay, so your off current increases. So your I off you will pay a price in your I off if your length you decrease. Okay, so we generally don't do that. We play with the W mostly. So can you tell me how R equivalent is it proportional to W or inversely proportional to W?
Inversely proportional.
So it is inversely proportional to W. What about C in?
Proportional to W.
This is proportional to W. What about CL?
Proportional to W.
CL does not depend on W, right?
Oh yes, yes. It's
Yes,
the
sir.
load side.
CL is the load. C
Sir,
in
but
again,
CL,
yeah.
sir, but CL is a indirect proportional to W, no, sir.
No, I am concerned about this only, right? I am concerned about this guy only. I am going to size this. CL is depending on W of something different, next stage maybe,
Okay, sir.
but not of this stage, right?
Okay, sir.
So C internal depending on W, this proportional to W. Fine. So this quantity does not at all depend on W because it is equivalently multiplying and dividing W. Fine.
Yes, sir.
Similarly, this quantity does not at all depend on W. So now I define this to be TP0, this to be F, and this to be gamma. So TP0 is 0.69 times R equivalent times C in. F is, this is defined as CL by C in, and your gamma is C internal by C in. So only W dependency come in this. Only inversely proportional to W. Fine. So this will help us minimize the formula, minimize the transistor circuit easily. We'll see that. So this factor is called self-loading factor. Basically, self-loading means your output by input of the output capacitances, output parasitic capacitance divided by the input parasitic capacitance of the same inverter. That is why it is called self-loading factor. This guy is called electrical fan out. You must have studied in your gate, in your logic gates, what is fan out? Number of outputs, right? With
Number
respect to
of
the
outputs an
input.
IC can drive.
Exactly. So this also, this F also makes sense, right? The number of how large a load it can drive. Basically, it is a CL, how large a CL it can drive. So this guy is called electrical fan out. Okay. And TP0 is called the intrinsic delay. Fine. So TP as a function of W is equal to TP0 times F as a function of W plus gamma. Okay. If that is the case, then in our question it was asked that we have this inverter chain. So this was the inverter chain, right? And CL is equal to 27 times of C1. So basically this is your A1, A2, A3. Fine. Now if I model it using this model, what will I see? This I will see as C input of 1, let's say. So it will have C internal 1, again C input 2, C internal 2. Similarly, I will have here C in 3, and this is CL, and there is also this is basically your CL plus your C internal of 3, because I can club these two, right?
Yes, sir.
So now do you see that this is the load for this stage 1, A1. This is the load for A2, CL for A2.
Yes, sir.
So if that is the case, so the total propagation delay, let's say I have some signal here, so it will take time to reach this point. This is, let's say, TP1, this is, let's say, TP2, and this is, let's say, TP3. So your TP will be TP1 plus TP2 plus TP3. So if I write this formula, so I will have what? TP01 times F1 plus gamma 1 plus TP02 times F2 plus gamma 2 plus TP03 divided by F3 plus gamma 3. Okay. I want to minimize it with respect to the transistor size, right? I want to minimize. Okay, I will come to that point. So can you see TP01 is equal to TP02 is equal to TP03 and gamma 1 equal to gamma 2 equal to gamma 3? Is this obvious to you, or is it not? Is this obvious to you or not? What is this? Let us go back to the
Yes, sir.
question,
Yes, sir. Yes, it's clear.
right? So why is it obvious to you that this will be the case?
Because there is seen term in both the equation. So
Because these quantities are independent of W, right?
Yes, sir. Yes.
Independent
Yes.
of transistor size. And we are only we are assuming everything is similar, just the transistor size will be different. We want to find out that transistor size. So can I write from this and this, TP is equal to TP0 times 3 gamma plus TP0 times F1 plus F2 plus F3?
yes, sir.
Fine. So what is F1? From this figure, can you tell me what is F1?
Seen one.
Is it
Yes, sir.
not?
Yes, sir.
Because this is my CL, right? For the first stage. Is that clear?
Yes, sir. Yes.
Similarly, F2 is C in
3.
3 over
C
C in 2. Similarly, F3 is CL
CL.
over C in 3, right?
So CL plus C in T3. There will be okay. So
No, because C int is different, right? So I have this for gamma. This is considered in gamma C in 3, right?
yes, sir. Yes.
Okay, maybe this is creating confusion. So what I'll do it C int 3 and let's keep it CL. So this is the load capacitance that we are talking about, right? C int 3 is basically your internal capacitance that is already considered in the case of gamma.
Yes, sir.
Fine. So now let's consider a general case of n stage. So just follow. If this from this equation, can I write it Tp0 n times gamma plus Tp0 F1 F2 Fn. Now this is Tp0 n times gamma. This is Tp0. So this is my C in 2 by C in 1 plus C in 3 by C in 2 plus, let's take some intermediate term because we need to generalize, C in j by C in j minus 1 plus C in j plus 1 by C in j plus tell your f of n. Okay, the point I wanted to make is that the C and J, or for that matter any capacitance, will come at two places in this kind of inverter chain. One is to calculate its own input capacitance, or its own your electrical fan out, and to calculate its previous stages fan out, right? So this is basically f of j minus 1 and this is basically f of j, right? So C and J is the capacitance or the jth element of the capacitance, input capacitance will play in two regions, or two electrical fan outs. So now what I want to do, I want to minimize this, right? How to minimize something? How do you find minima in a curve?
First order differentiation is 0.
So I will do CTP divide by partial derivative of C input of J. So this quantity will be 0. Similarly, every quantity will become 0 apart from these two because there is only where I have the C in J term. So what is the first quantity will give me? So it will give me simply 1 over C in J minus 1 and another quantity will give me plus C in J plus 1 times minus 1 over C in J square, and all other terms are 0 because that does not have any C in J term. So if for minima this is 0, so can you see Can you see this relation coming out of this?
Yes, sir.
That means
Yes, sir.
what? F of j minus 1 is equal to f of j, and j is true for any quantity. Fine. So now your CL by C in 1 is equal to what? C in 2 by C in 1
One.
times C in 3 by C in 2 times CL by C in n, right? Because I have n terms. So if all of them are equal, let's assume this is F naught. So it will be F naught times, this is first stage and this is nth stage. So F naught to the power n will be there. So how can you find out F naught? F naught is the nth square root of CL by C in 1. Fine.
Yes.
So in our question, it was given that CL by C in 1 is equal to 27 and number of stages we had is 3. So what is my F?
3.
F is 3. Fine. If F is 3, that means F is equal to what? C in 2 by C in 1 equal to C in 3 by C in 2. Because in all stages the electrical fan out should be same. And if your length is equal, then your W will be just 3 times, right? Where this is proportional to W, this is proportional to W. So W of 2 is 3 times of W of 1. So if this size is A, then the size of this will be 3A and the size of this will be 9A.
Yes, sir.
So why did I do the entire stuff? The entire derivation is because even if you are given at any arbitrary number of stages with arbitrary number of, for example, they can change this mobility ratio, right? Mobility ratio they can change some condition on this gamma, they can change some condition on this TP0. Okay. For example, they have given you different mobilities. Let's say it is not scaled by 2. Mu p is, let's say, 1 by 3 of mu n. Then what will you do? To calculate this R equivalent, you will just calculate R on P and you will calculate R on N and then you take the average value, because this is directly coming from the this equation, right? Fine. So this is how you basically size your transistor. So what was the main motto? Size the inverter chain in such a way that your overall delay is minimized. You must have seen, I am sure that you all have seen the this formula and then these formulas, right? But you should understand where it is coming from. This is coming from by minimizing the delay with respect to area of the transistors, of the inverter chain, relative sizing, right? So if that is okay with you, then in the next question it is asked that what is the minimum delay through the inverter chain. So what do we know? TP is what? TP1 plus TP2 plus TP3. So what is this? We have found out that this is TP0 times 3 times gamma plus TP0 times F1 plus F2 plus F3. So what is F? Again 3 raised to 27, CL by input is 27. So that will be 3. So this will be your TP0 times 3. What is your self-loading? Self-loading they have given to consider as to be 1. So this will be TP0 times 3 plus 3 plus 3 is 9. So it will be 12 TP0. Okay. Is that clear?
Yes, sir.
Okay. If that is clear, can you answer me this question? In a CMOS inverter, increasing the PMOS width improves something but also degrades something. So what we will do? We will just write the formulas of TPHL and TPLH. So 0.69 times HL is on resistance of what? NMOS or PMOS? Output is high to low. CL is
And
discharging through NMOS times CL plus
CDP
CDP
plus
plus
CDN.
CDN. Similarly, in this case, R on times P CL plus CDP plus CDN. Okay. So what I'll do, I'll club. So basically, this is changing with W. So this is changing with WP. This is changing with WP, and this is changing with WP. Okay. So we'll club out all the P whatever is dependent on W in one term and whatever is not dependent on WP in the second term. So in this case, we will have 0.69 times R on N times CL plus CDN plus 0.69 times R on N times CDP. Similarly here 0.69 times R on P times CL plus CDN plus 0.69 times R on P times CDP. So now again if we check, so this quantity, is it dependent on WP? It is not, right? So this is dependent on WP. So basically your this term increases with WP. Fine. That means TP HL is increasing with WP. If WP increases, TPHL will also increase. And what about this? So this is 1 over WP. This is proportional to 1 over WP and this is proportional to WP. So this term does not change with WP. But this, what about this term?
decreases.
This term decreases, right? So the overall TPLH decreases as WP increases.
Decreases.
So what does it improve? It improves TPLH, but it degrades TPHL. Is that clear?
Yes.
So, okay, let us now discuss about power. So let's say your input signal is something like this. Okay, and okay, let us say that this is your output signal. So these states are called, do you know the term? These states are called static states. Okay, static state means the time duration during which your output is not changing. Okay, that is your static duration. And what about these guys?
Rise time, fall time.
No, these states are called
Dynamic states.
dynamic states. Okay, or dynamic times during which your output is changing. Okay, the name itself conveys the message. So the power getting lost during this stage, these time durations are called, so this time durations power dissipation is called static power dissipation. Okay, and the power dissipation during these times are called dynamic power dissipation. Okay, so let us say, so let us mark this as 1, 2, 3. We'll analyze these 3 components. Okay, others will just, it is just simple. So let us say, let us be at 1. So let's say this is my inverter. So can you draw the, this is by the way V out, right? So can you draw the switch resistance equivalent circuit of this at 1? So
Yes,
what is
sir.
my output? Output is 0, right?
VDD.
That means I will have,
CL discharge.
not discharging. Why discharging? It is at 0, right? So V out is stable at 0. So I am at this point. No, I am at this point. So why it is discharging? It is not discharging at all. Output is fixed at 0 volt.
Yes, sir.
So what? So this is 0. So this node is 0. This node is 0. And let's say this is my R on N. And there will be this VDD. And ideally there is open circuit. So how much power am I dissipating in this cycle? What is
Half
the,
of the capacitance.
why, what is the capacity, what is the current in, so we are at stage 1, right? At stage 1 my output is fixed at 0 volt and the other terminal of the resistance is also at 0 volt. What is the current flowing through the resistance?
0.
So if the current flowing through the resistance is 0, what is the power dissipation through the resistance?
0.
So why are you saying that it is half CVDD square? So ideally static power dissipation should be 0 in CMOS circuits. Okay, that is why what we have seen for case 1. Fine. Similarly, let us be at 3. So what is 3? This is 3, right? What is my output in this case?
VDD.
So output is VDD. That means I have something like this. This is CL. This is V out equal to VDD. And this is VDD. And this is R on of P. So what is the power dissipation right now? So what is the ideally power dissipation? What is this? Come on, this is very easy, right? You have a resistance through which the power, see, passive elements, resistance only can dissipate power. Capacitance, ideal capacitances and inductances cannot dissipate power, right?
Yes, sir.
So what is the power dissipation in this case?
ID square in times R on P.
Why are you telling that? What is ID? What is ID? In stage 3, what is ID? Your voltage, output voltage, it at static position, right? That means it is not changing. It is
Zero.
having a value of VDD. So the resistance R on P has both ends at at voltage VDD. Why will there be a current flowing in this case?
Sorry, sir. Zero current will flow and it
So,
will be zero again.
so this is 0, right? So what we have seen, ideally CMOS circuits should have 0 static power dissipation. So that means if you have your mobile phone at an idle state, if you are not using it, so you will have no power dissipation. That means your battery supply will hold its value. That means with one charge, you can have much longer battery life, right? If you leave your phone at let's say 80% and then stop using it, after 2 days if you come back it should be at 80%, but that is not the case, right? The battery drains out even it at the static condition. Why does it happen?
Because of a finite I of value.
Finite I of value, right? So that means what does that mean in this case? Where am I making the wrong approximation?
At the NMOS site.
So basically this is not open, right? There is still an R off. In this case, this is an R of P. Fine. So as soon as there is a path, so current starts to flow because it is seeing ground here, right? This node is grounded, V out is 0. This is your phone's battery, right? Same thing is happening here. If this is VDD, there is a path of current flowing through this R off. So static power dissipation practically is not equal to 0, but very less in CMOS circuits. This is one of the major reason that in 1970s and 80s entire BJT game was dominated by or replaced by these CMOS circuits. Okay, the main reason is that in this kind of topology, what is the key concept? You do not have a direct path between supply rail and ground. Understand this very carefully. You do not have a direct path from supply rail or VDD to ground when the device is at its static operation. Okay, and static operation is the majority time it will be. You see, right, from 1 and 3, your 2 portion will be very less. It will be nanoseconds, but your static or idle time will be the most of the time your device is in. Yes, you agree with that?
Yes, sir.
So that is what is static power is, right? Now, so for our case, we will assume so far, we will assume P static to be equal to 0 for case of CMOS. So what is the other component? So let us be at region 2. Okay, so now we are going to study the dynamic region or the dynamic power dissipation. Fine. So there are, let's say, let me take, so your output is going from low to high, right? That means output is changing. So let me take this case then. So this is your CL, this is your V out, this is your VDD, this is your R on P. Fine. So can you tell me what power does this guy is dissipating? So power delivered by VDD, let's say instantaneous power is PT, will be equal to what? VT times IT, right? So VT is what for VDD? For this battery, what is VT?
VDD.
And what is IT?
VDS, sir.
ID. What is IT? The current through this.
Current, okay, sir.
So what is controlling the current? So see, you have to understand your basic RC circuits very clearly. Who controls the current in this case? This is a series combination, right? So the same current has to flow through the entire circuit. And what is the controlling element of the current here? This is your capacitance, right? That controls the dynamics of the current. So this will be C dV out
D,
T by dt, C dV dt, right?
yes, sir. Yes, sir.
So the total energy dissipated by this will be integration 0 to T rise time, right? This is, let's say this is 0, this is T rise. So t rise time P of t dt is equal to integration. Let's say dt will get cancelled, and your output is charging from, let's say at t equal to 0, V out is 0, and t equal to tr, your V out will be VDD. So it will be 0 to VDD, then VDD times CL dV out, right? So you can simply see it is CL VDD square. So that is the total energy delivered by the power supply. So can you similarly calculate what is the uh, energy stored in capacitor? The same formula you will use your VT. What will you use as VT now? What will be your VT now in case of capacitance? What is the voltage of capacitance
VDD.
here? It is V
VDD.
out, right?
V out, sir.
So V out, then dV out by dt, and there you will have your CL. So if you
Sir,
integrate
excuse,
it, yeah,
sir, I think V out by dV out by dV in, no, sir.
dV
Formula will
out,
be
sorry,
dV out by dV, no, sir.
why?
Sir, because the output is going inside, no, sir.
So this is the current IT. What is the voltage? VT, V out, V out of T. So what is your current? C dV dt, right? CL times dV is what? Voltage across the capacitance
Yes, sir.
by
dV by
dt.
dV.
So
Oh,
that is
okay,
what
sir.
I have written, right?
Okay, sir.
So
A
your E
little bit
capacity,
confusion over.
okay, not an issue. So if you calculate your capacitance energy stored, it will come out to be half CL VDD square. Right? Where did the other half power gone? Where has it gone?
Dissipated through resistor.
So how can you say that? You have to calculate, right? So similarly, energy dissipated by R on P is equal to what? Integration of what will be the voltage here? Voltage across R on. What is the voltage across R on P? What is the voltage across R on P? Hmm? If you want to find the power across this, you have to calculate it through the same formula, right? IT times VT. So you have just been reading it that half of the power will get dissipated. But do you know why half of the power is getting dissipated? So what is the voltage across R on? What is the voltage at the top terminal of the R on?
So voltage across R on VDD minus V out.
VDD minus V out, right? So exactly in the same fashion, if you integrate it, you will find that this to be half CL VDD square. Okay. So that is why your half of the power is dissipated, but you should know how to calculate power dissipated or stored across any element. It is the voltage across that element times the current flowing into it, and then you integrate to find the energy, total energy associated with it. So if that is you have understood, so now tell me what will be the power delivered, or let's say it is dynamic power. So you have the energy, right? You have the energy CL times VDD square. So how will you calculate the power? This is your energy. So you have a, let's say your output is transitioning from this and this. In this cycle, how much power is how much energy is being delivered by the output, by the battery? CL VDD square, right? P delivered or E delivered by the battery. And what about this case? How much energy is being delivered by the battery in this case when output is going from high to low? Did you get the question? When your output is transitioning from high to low, how much energy your battery supplies?
Zero, sir.
Exactly, right? Because what? This is disconnected, right? You have only this path for your discharge. So there is no power being supplied by the battery at that point, right? So to calculate the P dynamic, what we do? We multiply this by a frequency of 0 to 1 transition at the output. Means in 1 second, how many 0 to 1 transitions are there? Okay. So this is your P delivered dynamic for combinational logics. And what about for sequential logics? What is the sequential logic? So a combinational logic is some input is there, it will be just the output. But in case of sequential logic, you will have something that store the state and then give the feedback to the combinational logic again. Okay. So you'll have some memory action. And sequential logics are generally synchronized or triggered by clock. So basically, in case of sequential scenario, your P dynamic will be CL VDD square times, and there is also another property, F clock times probability of 0 to 1 transition. Okay. This is probability of 0 to 1 transition. F clock is the clock frequency, and other things remain same. Fine. This is what is the case for your sequential circuits. So by the way, what is clock frequency in your computer? Can anyone tell me what is the range?
Sir, 1.5 gigahertz to 4 gigahertz.
That is very low. Yeah. It is around the range of 1.8 to your 4.2, 4.3, right? Similarly,
Sir,
in high performance systems, for high performance servers and all, you can have till 5.2 gigahertz, right? Beyond that, if you increase your clock frequency, you will generate so much power and thus so much heat. Because see, this is what? This is the power that is being delivered by the battery. But there will be equivalent power being dissipated. So what will be your P dynamic dissipated? Dissipated, it will be just half of this, right? And this P to 0 to 1 is often also called availability factor or alpha. So this is what is dissipated. So how does this power being dissipated from the resistance? In what form of energy?
Form of heat.
It form of heat, right?
Yes, sir.
So if you increase your heat, so understand this very carefully. So you are at room temperature 300 Kelvin. Now you are increasing your clock speed. That means your power being dissipated from the resistance is increasing, right? That is converting to temperature because your energy is proportional to kT, right? 3 by 2 kT. If you take 1 degree of freedom, then it is half kT. So it is directly proportional to your temperature. So your temperature is increasing. So what will happen if your temperature will increase? Your mobility will decrease, your threshold voltage will take a toll, right? All the semiconductor parameters we calculate at one particular temperature. If we change the temperature, everything will change, right? For example, your device will start to become intrinsic. Your Ni, the 1.5 into 10 raised to 10 per centimeter cube is at room temperature. Now for example, you are doping it at 10 to the power 16 per centimeter cube. That means what? You have converted one almost insulator type of element to a conducting element. That is what your semiconductor is. Now, if you increase your temperature, the Ni or the intrinsic carrier concentration increases so rapidly, or it is increasing almost exponentially, so that your semiconductor is no longer a semiconductor. You cannot use it to turn on and off. It will just be a piece of metal wire, right? So you lose all of your good things of the semiconductors. So this kind of phenomena is called self-heating. That means current is flowing, temperature is rising. That again decreasing, making the current to decrease by decreasing the mobility and other parameters. Okay, and this heat will be so astronomically high that you cannot manage it in a small area of your laptop or PC. In case of your servers, you have a big area, so that is why they can go up to 5 and 5.2 gigahertz and not beyond that, right? And if you know that all the servers where this high performance computing are happening, they are at the very one of the coldest places they have kept it. For example, there is a server of Google or Apple, I am not sure, that is even under the sea to maintain the heat dissipation. So it is so high. Okay, this is why your clock speed has not increased over the decade, and that is why you have this your multiple cores, right? So what they have done, they have come up with a way that do some parallel task. We will not put load on one single processor. We'll distribute it into multiple cores so that your coding is also done in same way, that your blocks of the codes are run parallelly. So that is where the concept of multiple core came about. It is because they were not able to increase the clock speed. Okay, so clock speed plays a very important role in power dissipation or dynamic power dissipation. Similarly, now you are asked to calculate the circuit power dissipation. So understand very carefully, they have asked you about the power dissipation, not the power delivered or the overall dynamic power. So what do you will calculate? You calculate P dissipation as half CL VDD square time F clock times alpha. So your alpha is given as 0.2. So this is half. CL is your 150 femtofarad. Femto is how much? 10 raised to what?
Minus 15.
Into 10 raised to minus 15 times VDD square is 4. F clock is 2 into 10 raised to 10, 10 raised to 9, and alpha is your 0.2. So if you calculate this, it will come up to be 120 into 10 to the power minus 6 watt. Okay, that is your this value 120. And what about your VDD is 1.5? So your P dissipation 2 or VDD equal to 1.5 will be nothing but your 120 microwatt. What will you divide it by? This VDD square. That means your 4 times 1.5 square. So this will come out to be your 67.5 microwatt. Okay. So major thing to remember, P dynamics is proportional to CL, proportional to VDD square, and proportional to F clock. This is also one of the reason that your supply voltage was scaled down, right? Earlier you used to use 1.8 volt, 2 volt. Nowadays the supply voltage for this state of the art 2 nanometer, 3 nanometer transistors are around 0.6 to 0.7 volt, right? So we'll conclude with one more problem. So that is called, yeah.
In the previous question, you have said that the for the sequential logic, if the F clock and alpha comes, right? But in the question, it is said that for combinational logic.
Yeah, that is a catch. It should be sequential, right? So you understand, right? So in combinational logic, there is no concept
Yes,
of clock, right?
yes.
But even again, if you have some finite state machines and all, then your combinational block come in between two sequential blocks. So have you done the static time and timing analysis and milli state machines, Moore state machines, those kind of stuff?
So I have not done.
So you are at UG, right?
Yes, sir.
So I think they have included the static time analysis and computer architecture portion instruction sets pipelining in GATE itself from 2021. So you should check that, okay?
Okay, sir. We will definitely check.
Yeah. So that is one part. Yeah. So again, this is the same thing, right? The question is clock gating is used for. So most of the discussion I have done, right? Clock gating means your P dynamic is your CL VDD square times F clock times alpha. So you can reduce your F clock to reduce your P dynamic, right? But F clock you cannot reduce because that basically limits the speed of operation, okay? So there we need to find out some way out. So what way out we find out is that use the clock. So this is not good for speed of the system. So what way out we found is that use the clock only when instructions are carried out by the circuit. How will you do that? That means I am applying the clock and I will apply some control signal. Okay, let's say this is my control signal, this is my clock signal, and let's have these two connected in an OR gate fashion. So what does OR gate do? OR gate, just let me draw it, then you will be able to understand. So let's say this is your clock signal. So let's say this is your clock. This is your control signal is something like this. So this we call active period and this will call idle period. Okay. So what to, yeah.
Sir, if the answer is reducing dynamic power consumption only, sir.
Yes, the answer is reducing dynamic power consumption, but that I am explaining how it is happening. Okay. So what will happen in your active case? Active case is one input of the OR gate is 0. So that means what? Whatever is coming at this portion, the output will be that only. So at the output, you will have your clock intact. And what if my one input is 1? One of the input of the OR gate is 1. Then my output will be 1 always, right? Irrespective of the clock. So after this point, my clock gets fixed to a certain value. Now if I consider this overall system, so this frequency, I would rather use the term effective frequency, will be lower. This we call as gated clock. Why am I telling so? For sequential circuits, let's say your device is positive edge triggered, okay? So after this point, you will not see no positive edges, right? So if your sequential circuit is positive edge triggered, then this kind, or negative edge triggered for that matter, so your gated clock will help to reduce the dynamic power consumption by effectively reducing this entire term, right? You see the concept behind clock gating? However, if it is level triggered clock, then it will be a difficulty, right? So this is also one of the reason why we prefer edge triggering over level triggering, okay? Is this clear? What is clock gating?
Yes, sir. Clear, sir.
Okay. So, okay, logical effort I'll start next time. So any question? If not, so let us close today's session. Yeah.
Can you just explain about the direct path you are talking about in the when we are discussing the R1 and R off?
So when will there be a static power dissipation? For example, I do not have this, right? So is there a path between VDD and ground?
No.
So that means there will not be any current flowing out of the battery of your device. Okay.
Yes, sir.
So that means your static power dissipation or static power consumption is lower. Similarly, in this case, let's say you do not have your you do not have your R off. So is there a direct path between VDD and ground? So again the same thing, there will be no current flowing through it, right?
Yes, sir.
Because both the end is resistance. As soon as you make this current, no, so this VDD will start to discharge through this path. And as soon as this discharges, so this VDD voltage will drop and current will start to flow in this path. So your current is getting sucked out of your battery. So essentially we can say that if there is no path, direct path between this high rail and low rail, there will be no static power dissipation. That is the main objective of CMOS circuits.
Okay, sir. Got it.
Okay. Okay. Anything else? Let's close the session today. Okay. Thank you for attending.
Thank you, sir. Thank you.